has the limitation that only one thread can be actually running in the virtual machine at a time, and so it uses a global lock. So that simplifies a lot of the implementation, but comes at a fairly high cost. It uses pseudo preemptive scheduling, so every n bytecode instructions will switch threads, and any sort of external operations that are using I/O are going to release that lock and let another thread run. Unfortunately, over time, more and more of the implementation has depended on this feature. So reference counting obviously is a lot simpler when you don't have to deal with any locking, but a variety of other places, particularly where you call back and forth between Python interpreted code and C code that the user provided to extend the system, we're depending on the fact that there's an interpreter lock here to serialize access to the objects. And years ago, someone attempted to remove it, and sort of the implementation strategy we have just doesn't work at all in that environment. You have to change nearly every line of code, and the performance overhead is pretty high. So perhaps unusual about this bytecode interpreter, actually your screensaver is on, which obscures the clock. Has very heavyweight opcodes. So they often correspond to a source construct like look up this method or look up this instance variable. And they'll often call out of the main interpreter main loop into the Python runtime and do quite a lot of work. So most of the common opcodes run for hundreds of cycles. The cheapest opcodes just sort of stack twiddling, moving local variables between the stack and a frame executed perhaps 80 or 90 cycles, but still very expensive. So examples, I mentioned load attribute. Load global is going to look in several dictionaries for a name at runtime. And binary add corresponds directly to the plus operator, which could mean add two integers or add two strings or concatenate two lists. It has sort of the stack operations you might imagine. I mentioned briefly some sort of interpreter details. So the entry point is doing periodic checks for things like thread switching and for debugging and profiling hooks. And then very straightforward, decode an operation and its argument, and jump in the switch statement to the implementation for that method. There are a small set of opcodes that are going to branch directly back to the decode because they are themselves very lightweight, like a pop-top operation that just pops the top of the stack. It seems quite expensive to go back and do the checks at the entry point again, so it jumps directly back to the decode. And then a few other opcodes sort of predict what the likely next opcode is and try to jump directly to them rather than going through sort of a generic decode. So, for example, if we do a comparison operation and they're equal, then we expect that the next operation, most of the time, is going to be some sort of jump. So we'll try to decode and go directly to that jump operation. And the consequence is that it saves a few hard-to-predict branches. And these sort of small twiddles to the interpreter loop over the last couple of years have sped up sort of standard function-intensive benchmarks 20%, I'd say. So then I wanted to go into detail of what a binary add operation does. It pops a couple of arguments off the stack, and it has two inline cases that are executed in the main line of the virtual machine interpreter to look for exact integers, and if they're exact integers, do actual integer arithmetic and replace the top of the stack with a new Python object, assuming that they haven't overflowed. Does a similar sort of thing for exact strings, where we're just joining two strings with the extra property that will actually call out to a C function to do the concatenation. Anything that doesn't fall into those categories, or if there's an error in string concatenation, or if there's an overflow in integer arithmetic, goes through this very generic routine that does all sorts of coercion and lots of checks to see if either type has a custom slot for handling addition that might know how to coerce the other side. And if none of that works, then it will say, well, maybe these were sequences, and we'll try to put two lists together. So there's really a lot of code getting executed for a binary add. It's all untyped. Function calls are also very expensive, so the frames are heap allocated. So in theory, we wouldn't need to use the C stack at all for function calls, but in practice, we actually do make a recursive C call to get back into the interpreter loop and reinitialize it. that makes it easy to provide good debugging support when something goes wrong, but is otherwise somewhat wasteful. There's a variant implementation called stackless Python that sort of does the natural thing and gets rid of the recursive calls to the C stack most of the time. Another reason function calls are slow is that there are a lot of variations on calling conventions, so you can provide a variable number of arguments and keyword arguments and default values, and the various checks to decode the arguments and initialize the frame from all that are very expensive. Lots and lots and lots of hard to predict branches and very expensive. So another interesting thing is that very often you call from the Python runtime back to C, so you, back and forth with C. So you do an addition, you get into the C code for binary add, and you find that one of the two types has a method implemented in Python that's going to do something custom for addition and try to coerce the other type. So you're going to call back into the Python interpreter recursively. With C, relatively straightforward, but it's delicate to maintain state, particularly for reference counting across that boundary. It can add a lot of C stack frames as you get into the PyNumber add implementation and realize you're going to go back to Python. So it sort of limits the size of the Python runtime stack. And it's occasionally very hard to propagate errors. So you get to a point, I think an example would be a finalizer, where you start running a finalizer that's sort of in Python and you realize it has an error. And you're sort of at a point in the garbage collector where the garbage collector really is not interested in hearing about that. There are a variety of cases like that where it's difficult to handle error cases. And hard to predict effects. So one thing that has to be guarded against a lot is sorting a list where the comparison operators are overloaded, such that someone could accidentally modify the list that's being sorted. So there's a lot of hair in the interpreter to deal with those sorts of cases. So IronPython, which was implemented in a few months and runs on .NET, is a pretty interesting comparison because, in general, for most things, it's faster than the C implementation, although it's smaller and young. So Python has sort of a dry stone style benchmark, translated from Ada to C to Python over the years, and IronPython is a lot faster on that particular benchmark, which is primarily function call intensive. The biggest benefit, so the 80% side of that benefit, is by using native CLR frames instead of creating these Python frames virtually. That gives up some ability for introspection, which I for one would be happy to give up, but limits debuggability and things like that. Another example of where IronPython is much faster is that non-local name lookup is much faster because he actually does some static analysis to determine what the names in all the modules are, so that they can be looked up directly via the .NET runtime rather than falling back to sort of this hash table lookup at runtime. Although it has hooks to support all the sort of tricks one might want to do with the hash table lookup. The one interesting thing is that in comparison, if you look at micro benchmarks on .NET that just create lots of small objects and delete them, create a list of 10,000 integers and iterate through them and then free them, or initialize the large list with small objects, that is generally a lot slower. At best, it will run at 70% of Python speed, but for some of these list operations, it's running a tenth the speed of CPython, which sort of makes us think that the custom memory allocation tricks that playing in the standard interpreter are actually buying something for us in that case. So if I look to the future of Python, the interpreter issues that are raised most by users that I talk to are ones of performance. So Python is great if you can afford the performance hit, and you can mitigate that to some extent by sort of agreeing that you're going to have to write some things in C if you want it to go really fast, and work in an environment where that's easy to do. But in general, you'd like it to just go faster all the time and not have to write anything in C. The other problem is security, which is, of course, a problem in these end-user applications people are developing, where people can load plugins and custom things, and we don't have any encapsulation. So, really, we don't have any story to tell them about security. The application server I worked on did this trick with proxy types implemented in C, where you had one generic proxy that could look like any Python object, but could be loaded with a policy that turned off access to certain sets of variables. So that's a mechanism that exists, but it's sort of extra linguistic and not particularly satisfying. So if I look at sort of how all those issues, sort of manifest themselves among the developer community, I personally think it's not much fun to implement Python in C. I think sort of the initial success with IronPython suggests there's a lot to be gained by targeting a higher level underlying platform, whether that be a .NET runtime or an LLVM runtime or something else, and handing off responsibility for some of that work to someone else. I think it's clear we need sort of a better runtime representations of objects and namespaces that are more amenable to some sort of dynamic optimization. The fact that everything is only just a hash table makes it really hard to even do dynamic optimization at runtime. So, doing sort of a more traditional object layout with perhaps some sort of fallback mechanism to accommodate the dynamic things that some users do would make a big difference. And I think the sort of single-threaded interpreter approach is just going to be a growing liability over time. Sort of 5 years ago, most people had uniprocessor boxes, and the fact that this lock was released and all the blocking I/O calls made it sort of a modest effect. But as you get more and more processors in your boxes and more threads running on your processors, it doesn't seem a tenable long-term solution. So I think. That's all I wanted to say. We have time for some questions.
Question about introspection. I'm actually not a Python user. A good friend gave me a demo, and what he was most jazzed about was when they got their implementation was written in Python, and when they got that bug report from the field, there was this beautiful stack trace.
Right.
Variables, values, the whole works. Now, is that lost in IronPython, or do they preserve that?
I'm not sure. I imagine that there are two variants of IronPython. So I said in the slide, it's